Welcome to the pre-recording of lecture 25 on pipelined computations. So our lecture 24 was the midterm exam. Pipelined computations are extremely useful to introduce parallelism, where at first there might not be any obvious parallelism possible. So I will, in the first part of this lecture, introduce some examples and terminology. The speed up can be optimal for many instances. Parallelism also is already happening even if you don't know it. That it happens, I will give an example of loop unrolling. And the second part of this lecture is then more going to practical examples, or the examples are actually not practical, but mostly how to get started with a pipelined computation. And in this lecture we will come back to message passing. Okay, so here is one of the main applications of pipelining in the manufacturing of cars. So building one car is a very sequential process, but building many cars can actually happen in parallel. So for oversimplification, we assume that there are three processes or three stages in the manufacturing process: the assembling of the exterior, the fixing of the interior, and the paint and finish. So these are these three stages that are shown as P1, P2, and P3. The stages or the processes or processors each execute different tasks in this manufacturing process, and they work on many instances. So here in the example, also oversimplifying, we are going to manufacture 5 cars. So the first car, C1, gets assembled, its interior fixed, and then painted and finished. So it takes 3 time units to finish one instance. But while the C1 moves up through the assembling of the exterior, when that is done, then P1, the process that assembles cars, can already start on the second unit. So what the space diagram demonstrates is that it takes 3 time units for the first car, but after that every car takes only 1 time unit. So we are producing 5 cars with 3 stages. So this would take 15 time units. But now you can see that we can do this in 7 time units. So 7 over 15 or 15 over 7 is a speed up of more than 2 with 3 processors. So already on this very simple example, we can see the benefit of pipelining. Here is another example from signal processing. We have again 3 processes to process a signal via the fast Fourier transform, then the filtering. So here, for example, removing the low amplitude. You could also remove certain frequencies. And then we reassemble with the inverse fast Fourier transform the filtered signal, the original signal. Um, with the space-time diagram, so now it is shown in an alternative fashion. So the space goes down. So we start out with the first signal. We compute its, or actually, we have one entire signal, but it gets broken up into pieces of each the same length. And also here, essentially, we assume that every stage in this pipeline takes the same amount of time. So even though this looks like a very sequential process, you can see that if we were doing this sequentially, it would take again 15 time units, but now we can do this in 7 time units. Okay, let us generalize these two examples. So we speak of a p-stage pipeline. Well, p is the number of processors in the pipeline. How long will it take to process n inputs? Well, it takes p time units for the first input to be done. And after this first item is done, the remaining n minus 1 items only occupy 1 time unit each. So we have a parallel execution time of p plus n minus 1 time units. So that is the entire time it takes for the pipeline to complete n inputs. A time unit is also called a pipeline cycle. There is the pipeline latency. That is the time it takes, the waiting time, for the pipeline to be fully productive, to run fully in parallel. So let us compute the speed up. So the sequential time is n times p. So in the examples we had 5 was the value for n, p was 3, so 15 over p plus n minus 1. So 5 plus 3 minus 1 was 7. So the speed up can be computed very straightforwardly. Now you can see that in the limit, as we have a fixed number of processors, typically, usually, but the number of items can grow unlimited, and by taking the limits, the dominant term is n, so the p minus 1 term in the denominator then becomes negligible. And that's one way how you can evaluate the limit, justify that in the limit, when the number of inputs is significantly larger than the number of processors. Again, the scalability question that we have considered in this course already many times. You can see when we look at the limit that we have an optimal speed up. So it's called a functional decomposition method to develop parallel programs. In the classification of FLIM, we have one single data stream, but multiple instructions. So quite different from the single instruction, multiple data from the GPU acceleration. But actually we have seen pipelines also over there when we considered the memory hierarchies. So pipelining is a very universal concept to make parallel programs. So it's even applied when you're not really aware of it. So consider the floating point addition. So the floating point addition consists here in a simplified model. If you would do this in a numerical analysis course, it's a very great exercise to actually do this by hand to see what is involved. So the floating point numbers are represented in a packed format where you have the sign bit, the exponent, and the fraction. One needs to unpack this and compare the exponents. So the number that is smallest of that number, the exponent gets adjusted, and the fractions are then aligned. Before then we can do the fractions, the addition, then we normalize the result, and then we must again store the result in the packed format. Here on the example, the 32-bit format. So it takes at least 6 time units for doing one floating point addition, but previously when we examined performance, we could observe that actually, theoretically, in one clock cycle, there could be one floating point addition done. And why is that? Well, we have pipelines, so we have a 6-stage pipeline. If we have many numbers to sum, so we have 2 vectors to sum, so then instead of 6 times n operations, we can do this in n plus 6 minus 1. So the 6 minus 1, this 5, become negligible for when you're dealing with very long vectors. That's why in linear algebra, most scientific operations are involving linear algebra, one can realize the one floating point operation per clock cycle. That's why we may often assume that with a good implementation on a gigahertz processor, we will have gigaflop performance. Okay, so here is a more complicated picture that I stole from the Intel Architecture Software Developers Manual. And now you can wonder, as a software developer, why would I actually need to bother about this? This is way too technical and actually perhaps not entirely relevant. The specifics are not relevant, but let me give a very simple high-level example why it actually matters. Even if you are not doing any obvious parallel programming, you are doing it. So I took this example from this textbook here, Scientific Programming and Computer Architecture. So it is a fairly recent book. The author explains in great detail what you need to mindful of when you want to develop programs that are efficient. I took the inspiration for the following example, the approximation of pi via a very slowly converging series. It's also a motivation to apply extrapolation methods, but I will use it to demonstrate loop enrolling. And while C is indeed still a great language, and C++ to get the most performance, we can already illustrate the main point in Julia, which is one of the official languages in this course. Okay, straightforward. So at the bottom of the slide, you see the sum, and we have the even terms and the odd terms. So in the odd terms, we subtract. In the even indexed terms, we add. And the denominator increases each time. So you see the formula, there's only one formula, essentially. But there is this branching. So we have the if test that tests whether the index is even or odd. Now, if you execute this, then this gets executed by a processor, and the processor has to always look at this integer division for the index, even and odd. So, and at the same time doing the floating point computations. So the pipeline for the floating point operations actually does not really work out very well here. Also because we have different instructions. So we have a minus and we have a plus sitting there. Now it could very well be that on some processors there are multiple, on some chips there are multiple floating point units, and you could imagine that the minus and the plus could be going to separate ones, but it's very hard for a compiler to figure this out. So this is a straightforward implementation, and as we will see, it's not really an efficient one. We can rearrange the code to actually avoid this if test by summing first all the even indexed terms in the sum, and then subtracting all the odd terms. So in Julia, this is a very straightforward computation. You see the looping, so the increment for every loop is now done by 2, and the if test has disappeared. So in some sense, we have also a simpler program. So the correctness of this program can still be very easily verified, as is done at the bottom line. It is high level, and if it wouldn't be from what we have covered so far and from the context, you would not really know that this is a program that is much better suitable for parallel computation. So this is the highest level form of parallelism that we have done so far in this course, except from calling software that was already running in parallel. Okay, benchmarking. So I'm doing this on our Pascal computer. And you can see that it's almost twice speed up that we have. So we go from 239 milliseconds to 125 milliseconds. Okay, so even if it's not entirely obvious that we are doing parallel computing, we are actually doing parallel computing. And as a programmer, one needs to be aware of what happens with the floating point instructions. Okay, so that is the first part. In the second part, I will go to some very basic toy examples, or in some sense preparing for actual pipelined implementations. Let's consider a ring topology. So a ring topology is in some sense a very natural way to implement a pipeline. So we have the processors lined up in a ring. So every process sends to the process that has one index larger, except for the last processor sends to processor 0. And the receiving happens from the processor with one index less, except for the first processor P0, which will receive from the last processor. So there is this mod P instruction, mod P, when we compute the destination of each send. And one has to be careful, of course, the receiving. So here in this high level organization, I said it's a manager-worker organization. The manager is still responsible for the input, receiving the input, and the output is also handled by the manager. So this could also be functional decomposition. What the node 0 does is mainly handling the input and the output. The other nodes, P1, P2, P3 here, are the worker nodes. So it is still a hierarchy, a ring topology. One can think about, we have seen the fan in and the fan out broadcast. One can actually think about hierarchies of processors as well. So it would be possible to consider other topologies. So if you have the hypercube topology, we have seen that the hypercube topology supports the fan out. So one could build a hypercube topology also with pipelining. But here the ring topology is quite suitable. The example with MPI, so I will give the code, I will show the code. So here is how it is run with one instance, where every processor, every worker will double the number. So the first processor receives 2, multiplies that number by 2 and sends the 4 to processor 2. Processor 2 receives the 4 and from node 1 and will double it and send it to processor 3. Processor 3 will double it once more, so we now have the number 16, and that will be sent to the node 0. In the classification of pipelines, we talked that we label this a type 1 pipeline. So all pipelines that we have seen so far will not have any speed up if there's only one item to compute. So that's one characteristic of a type 1 pipeline. It's also the case, and that is caused because one pipeline cycle must be completed entirely before the next cycle can start. So here are space-time diagrams for type 2 and type 3 pipelines. So you see in type 2, the second process can already start before the first process has completed entirely. So you can see from the space-time diagram that there is already speed up there. In the car manufacturing, so we split it off, the exterior assembling and the interior, but one could already do something with interior in a car that is not yet fully assembled. So the windshield wipers, putting them on, and you can already work on the interior simultaneously on that. So it's not too hard to come up with examples, and actually most of the pipelines will actually be of type 3, where the processes are overlapping and they are also different in time. So the type 1 pipeline was actually a very first example, easy to analyze as well. Okay, some MPI code. So here is the code for the manager. So we are now again into the C world. We have a single program that's executed by multiple processors. Here what the manager does, the manager is responsible for all the printing. So it reads, it's an interactive number, it will read a number, and it will also print a number. So here you see the viewpoint from the manager. The manager will process the input. I flushed the output buffer. And the manager will send the input and receive the output. From the perspective of this program, it looks as if the manager only does one send and one receive. So it's important to note the destination. So the sending goes to 1, the receiving goes from P minus 1. So for MPI, again, it was important, or it remains important, that every send is matched by a receive. So the destination 1 here must have a receive, and the P minus 1 node must have a send, otherwise the manager is blocked. So these are also examples of synchronized computations. So this also fits within the classification of computations that are synchronized. Okay, every worker will receive a number from the previous processor. And here there's a lot of printing, but there's only one instance that gets through, so we will run this program only for one instance. So, and the printing is done to verify the correctness. So there is the receive from the previous program, from the previous processor in the pipeline, in this ring topology. So it is a ring topology because if the processor identification number is P minus 1, then the send happens to the manager, the node with identification number 0. And before the send, there is the doubling of the number. Okay, so that was the ring topology. Let's now apply this in an example where there is potentially parallelism. So we will consider the pipelined addition. So in some sense, this is rather strange, but it could be a template for computations that are not so awkward. So this is functional decomposition, but we apply data partitioning. So we have 32 numbers to sum. So in some sense, this is also now a sequential computation, one after the other, but we are applying the data partitioning, so the sum of 32 numbers gets broken up into 4 different pieces: A, B, C, and D. Why is that important? We will see sorting in the next lecture. One often applies parallel computation, or with multiple computers. You can imagine that you would work with a very large data set, and it would be not possible to have the entire data set in one processor. So you can think of a very large distributed database as well. The pipeline will actually do something with these numbers. So every processor now does actually 7 additions with the 7 numbers that are available, with the 8 numbers that are available at every node. Okay, um, here we have the sums. So we have the um, sums that are going in. So you see the notations. So the A sum is first being computed. Um, so we have the A sequence that goes through the four processors. So A1 gets computed, which is A naught plus A1. Then the next processor starts with B naught plus B1, while the processor P1 adds to the sum A2. So the capital A2 is the sum of the first three A numbers. A3 is then computed by processor 2, while processor 0 and processor 1 are also summing, but then on different parts of the total sum, the C partition and the B partition respectively. So after 3 time units, so this is the pipeline latency, all four processors are adding up. So the first processor P0 is then already busy with the first two numbers from the D sequence. So the D sequence that then also gets through the pipeline. Okay, so there is some extra notation that is needed. So the pipeline stops, so we have 32 numbers. So after D7 is computed, so the A7 does not need to go from processor 0 to processor 1, so it stays on the processor 0 in this ring topology. And at that time, the processor 0 will accumulate the final results. And you see that there is still parallelism possible there. So while the processor 0 is accumulating, adding to A7 the B7, the other two of the other processors are still working on D7. P2 is working on D7, and P3 is working on C7. So D7 essentially does not change anymore, but we have this ring topology. P2 will not send directly to the processor node 0. Okay, in total there are 12 time units here, but the sequential time would have been, we have a sequence of 32 numbers, so this would have been 31 additions. Okay, so a significant speed up, more than 3 even on this very simple example. Now, of course, in this example, it's too small to actually have to observe any actual speed up. Everything will be occupied by the communication overhead here. All right, so the analysis. So we have to do 31 additions. So there is the n-1, the 31 operations, or n-1, the sequential time. The parallel time, we have the parallel latency sitting in there. We also have the extra last addition. So the processor 0 needs to wait one extra cycle. So in the denominator, we do not have the p-1, but we have the p. Okay, so you see that in the limit, as n is again growing, the p term in the denominator becomes negligible. Also the -1 in the numerator we completely ignore. And we have then the optimal speedup when the number of data elements, the number of inputs, is way larger than the number of processors. So typically we work with a fixed number of processors. Okay, so let us now look at the output. So this is a very good programming exercise. The program is defined in C. An obvious exercise is to provide an MPI for Pi version or a Julia version with MPI.jl. So that's another way to learn and appreciate high-level languages. The logic itself is defined here. So you see what happens. So there is essentially not much parallelism because of all the print statements. So you see the sequences of the numbers. So we have a fixed sum. So here we have 30 numbers. I think I took the number of, so I have the number of processors, but then also the multiplication. So it might be that the program might not still be quite in general. Okay, so I'm sorry here. So we have the sequences. So this is synchronized. The numbers that are passed. So we have these subsums that are passing, and at the end we have the final sum. So I probably most likely arranged it that there were a fixed number of steps that were going to be done depending on the number of processors in the pipeline. And indeed, we have the pipeline sum. Everything is done in one function, the pipeline sum. Here it's executed, so P is the number of processors. The number of, so I had on the example 5 processors and 30 numbers, so 5 times 6. We have the identification number I, so I equals 0. That is the code for the manager. So the manager will generate the sequence of numbers. So the numbers are stored in a matrix. So there is this matrix of numbers, which made it somehow more logical, convenient. So we have the data that is being summed. So the numbers are actually stored. You can see the linearization in the print statement. So that is the first step, what the manager does. The manager is responsible for the generation of the input. Then the manager code continues, starting the pipeline. So we have this matrix, and there is the cycle. So in the notation I had the A, B, C, D sequence. Here I have the sequence n for j equals 0 up to j equals p minus 1. So we have the sending and the receiving. So we send in this pipeline, we send the destination is 1 and the receiving comes from p minus 1. So we are respecting the pipeline topology. Each time the number, so it looks a little bit contrived, a bit artificial, but it's actually not entirely. It's quite logical, because you see the manager sends p numbers and receives one number back. So receives the sum. So in some sense, it is not entirely. It's not completely. It's of course completely natural and logical. You get the parallelization of the sum. So the manager sends it through the pipeline, all the numbers that wants to be summed, and receives the sum back. Again, this is done with the ring topology. Another exercise would have been with the hypercube topology. Then what do the workers do? The workers receive numbers, and it's in the hierarchy. So the farther that you are in the pipeline, the fewer numbers you actually receive each time. You do the addition. So the data movement is quite extensive, but the arithmetical intensity stays only, every processor there's actually only one operation on the data. So on the Jade sequence, adds the first with the second. The pipeline topology we send to the next processor, except the last processor sends back to the manager. Then the manager has these stages, so still the pipeline latency, so it's now at the end. So you can see here that there is still parallelism. So it looks as if the manager is still doing p-1 extra steps, but during these steps the other processors are still working. Okay, so this is the ring topology performing on an addition. So this is a flashback on what we have covered earlier on in the course with MPI. It's a good exercise to work on MPI for Pi implementations or Julia implementations. Okay, so there are some exercises that are written down here. If you have been a TA for a large lecture, then you must have been a processor, a grader in a pipeline. So pipelining has, of course, the benefit that it allows for specification. So in the grading of an exam, you could specialize in that one particular question. It also allowed for fairness in the grading. So explain the speed up that you get from this. So rather than doing this sequentially, one person who would pass all the exams in its entirety to the next person for grading, and that would be a sequential process. If you come together in one room, then there's a lot of close to an optimal speed up that can be done. So we've seen the doubling of a number for one number. So I was introducing the ring topology in that way. Do this with doubling the numbers for 10 consecutive numbers. So doubling is a very trivial application. It's just shifting of bits. But again, you could think about a more computing intensive operation where you would replace this by a complicated function when you would do numerical integration, for example. Horner's method to evaluate a polynomial. Here it's natural to work with a pipeline, so initially you see you have a multiplication by x and then an addition. So at first, when you solve this exercise, think about a two-stage pipeline. But one can generalize this to a p-stage pipeline. Okay, so I hope that this lecture was interesting and not too confusing. We will continue pipelining when we consider sorting. And the main benefit there with pipelining, with distributed memory computing, is obviously the large data sets, distributed database. For shared memory, we have the introduction of extra parallelism, so the functional decomposition, where you could have the pre-processing, the post-processing, and the processing and the post-processing as a very natural three-stage pipeline.